Dear students, welcome back. We are now doing the higher order ordinary differential equations. In the previous lecture, we had seen some kth order linear differential equations, and we had talked about the solution space of linear homogeneous equations and the linear independence and linear dependence of solutions. In this lecture, we are going to kind of characterize a property to verify the linear dependence and independence of solutions of an ordinary differential equation, and we will also introduce the technique of reduction order, in which you can find out a linearly independent solution given a solution. Okay. So let's start with the definition of what is called the Wronskian of Wronskian of a collection of functions. So suppose you have a collection of functions u1, u2. Okay, suppose you have a collection of functions u1, u2, uk, which are all k minus 1 differentiable functions. Okay, so you have k collections of functions, and each function, each ui is k times is k minus 1 times differentiable functions. Okay, in its domain, let's call the domain as I closure. Okay, then the Wronskian of this collection is, which is denoted as w of u1, u2, uk, and so on, is defined as the determinant of this matrix. Okay, so this is a k cross k matrix, if you notice, right? So there are k rows. So this is row 1, which is just the functions, which is the given collection. Then its derivative, row 2, which is first derivative, second derivative in row 3, and so on up to k minus 1. So in total you have k rows. Okay, similarly in the column you have the k collections, right? u1 to uk, right? So you have a k cross k matrix. So Wronskian is nothing but the determinant of this matrix. Okay. What is the motivation for this definition? If you recall the example, at least one example that we did in the previous lecture to verify the linear independence of x and x square, if you recall that. Let me just show you that. Yeah. So if you recall this example here, we had to show that x and x square are linearly independent. And how did we show? So to show linearly independent, we have to look at this linear combination, alpha 1, alpha 2, and we have to show that if this linear combination is equal to 0, then the alpha 1, alpha 2 should be 0. And how did we show this? If you notice, we had, so suppose you call this u1 and this u2. So the x is u1, so the function u1 of x is x. So you have two collections here, x square. If you recall this, then what we have done here is that you have alpha 1 u1, alpha 2 u2. And then what did we do? We differentiated. And finally, what did we get? We got alpha 1 u1 prime, alpha 2 u2 prime. So if you think of these two equations, okay, what you have done is actually u1, u2, u1 prime, u2 prime, alpha 1, alpha 2 equal to 0, 0. Right? That's the system of equation that you had. That's what. So you did something like this, and then you manipulated the second equation, then you solve for alpha 1, alpha 2, and finally you show that alpha 1 equal to alpha 2. So the point I'm trying to highlight here is that to show the linear independence or dependence, you had to differentiate and you had to actually look at this matrix equation, right? So that's, and you see this is precisely the matrix whose determinant is Wronskian, right? Am I right? Okay, so U1, I don't know, it's U1 prime. Okay, this is U2 prime. So you have this matrix, this is Wronskian, and that's the motivation for the definition there. Okay, so what is Wronskian? If you have a collection of functions, okay, then you write down this K cross K matrix, and the determinant of that matrix is the Wronskian, and you notice that this Wronskian itself is a function of X, right? Because U1, U2, Uk are all functions of X. So you can write down this matrix for each fixed X. So if you write down this matrix for each fixed X, you have a matrix for each X. So this Wronskian is actually a function of X. So in fact, you can think of Wronskian as a map from the domain of U, U1, U2, right? All the U's domain of U to R. Okay. So this is Wronskian. Now, why did we define Wronskian? We are going to kind of characterize the linear dependence and independence via the Wronskian. So the first theorem is this: two functions U1 and U2 are linearly dependent in I if they are linearly independent. If U1 and U2 are linearly dependent in I, then the corresponding Wronskian is 0 for all x. So you see, I said it's a function of x, right? So for all x, it's 0. This is the theorem. So if you have two functions, if they are linearly dependent, then the Wronskian is 0 for all x in the domain. Okay. Now, if you remember this logic property that if P implies Q, what does P implies Q? If P happens, then Q happens. Okay, this is a logical statement, right? If P implies Q, then you know from logic that not Q will imply not P. So if P happens, then Q happens. This means that this also implies that if Q does not happen, then P does not happen. Because if P happens, then Q happens. Right? So this statement here, that if U1 and U2 are linearly independent, implies that the Wronskian is 0 for all x, also means is that if Wronskian is non-zero for some x, so the opposite, so the opposite of this, that Wronskian is 0 for all x, opposite of that is not of this statement, is Wronskian is not equal to 0 for some x in I, not all, because here it's all. So not of that will be for some x it is non-zero. So if it's 0 for all x, opposite of that will be it is non-zero for some x. So if this happens, then U1 and U2 are linearly independent. Okay, so this theorem gives you a way to check linear independence of two functions, right? If you take two functions and if you compute its Wronskian, if that Wronskian turns out to be non-zero for some x in the domain, then the two function has to be linearly independent. So let's prove this result. So you start with U1, U2, and it is given to us that they are linearly dependent in I, right? The statement. We need to show this for all x. So because it's linearly dependent, there exists right? By the definition of linear dependence, there exists non-zero alpha beta such that alpha 1 u1 beta u2 equal to 0. Okay, this is by the definition of linear dependent. So now you differentiate this equation, so you get this matrix. So if you differentiate, what you get here, you will get alpha 1 u1 prime plus beta u2 prime is equal to 0. Right? So this equation and this equation becomes this matrix equation. So the matrix on so we have this matrix equation. So we have this matrix equation that u1 u2 u1 prime u2 prime alpha beta is equal to 0, where this alpha beta is a non-zero pair, right? So at least one of them. So at least one of them is non-zero, alpha and beta. So you have a matrix here which for a non-zero vector is 0, right? Which means what? Which means that the determinant of this matrix has to be 0 because the kernel contains non-zero elements, right? The kernel of this contains non-zero elements. So the determinant of this matrix should be 0, and it should be 0 for all x because this property is valid for all x. Right? This matrix equation is valid for all x, right? So the determinant of the matrix should be 0 for all x. So we have proved this. And this statement is just a consequence of this statement because P implies Q, so not Q implies not P. So what is P? Linear dependence. Not P is linear independence. Okay. Okay. Now, so now in this statement, the converse is not true. So suppose the Wronskian is non-zero. Suppose the Wronskian is 0 for all x, then that does not imply that u1, u2 are linearly dependent. See, this is true. If it's non-zero, it implies that it is linearly independent. But the converse of this statement, and hence the converse of this statement. So the converse of this statement is not true. That is, zero Wronskian does not imply that the functions are linearly dependent. Okay, and that's an example that we are giving here. So let's take these two functions, u1 which is x mod x and u2 is x square. Okay, in fact they are more or less, you see, they are same because x square is x dot x, whereas this is x mod x. So the only difference between this and this is that here you are multiplying always the positive function, whereas here you are multiplying in the same sign. Okay, so u1 is x mod x, u2 is x square. Now these are two functions which we have taken. So the derivative of u1 prime, right, if you differentiate that, right, is 2 mod x, whereas u2 prime is 2x. Okay, so you can differentiate this. You can apply the derivative formula, and you can compute that the derivative of this function is differentiable and derivative is 2 mod x. Okay. Now its Wronskian is 0 everywhere, right? How do you check that? What is the Wronskian? X mod x and x square, 2 mod x and 2x, right? And this is, as you see, it's 2x square mod x minus 2x square mod x, which is 0, and this is true for all x, right? So the Wronskian is 0 everywhere. Okay, so the Wronskian is 0 everywhere. Now this is an example. So now this is a counter example for the previous theorem, right? I mean for the converse of the previous theorem. So what we will now have to show that u1 and u2 are actually linearly independent, right? But u1 and u2 are linearly independent. How do you verify this? If you take this linear combination alpha u1 beta u2 equal to 0, right? Then for x less than 0, that is when x is negative, mod x is positive, whereas this x is negative. So this x mod x, this is negative of x square, right? Whereas this is beta x square. So what you get from here is that beta minus alpha is 0 when x is negative. Now when x is positive, this is positive, this is positive, so this is x square, you have x square, so you get alpha plus beta equal to 0. So the alpha and beta that appears in this linear combination should satisfy both this condition. The first condition gives you alpha equal to beta. The second condition gives you 2 alpha 2 beta equal to 0. So from here you can conclude that alpha and beta are 0. Okay, which means that the given function u1 and u2 are linearly independent, whereas the Wronskian was 0 everywhere. Okay, so the converse of this statement is false. Wronskian. So we have showed an example where the Wronskian is 0 everywhere, where the functions are linearly independent. Okay, so the converse of this statement as such is not true. Okay. But the converse is true if you have an additional condition that the two functions or the k functions that you have are solutions of an ODE. Okay, if you additionally impose that the functions are solutions of an ODE, then the converse is true. Okay, so the statement is here. If you have k solutions u1, u2, uk of a kth order linear homogeneous ODE, okay, Ly equal to 0. So L is the L is the ordinary differential operator. Okay, so Ly equal to 0 in I, then these u1, u2, uk are linearly dependent if and only if. What is if and only if? Both happens. That is, P implies Q and Q implies. So this implication is also true. This implication is also true. Okay, and this implication we have already proved in the previous theorem. This implication we have already proved in previous theorem. This is the implication which was not true earlier. Now with this additional condition that they are solutions of an ODE, this implication also becomes true. Okay, so linear dependence if and only if Wronskian is 0, but here the small change is that earlier it was for all x, now we say for some x. Okay, so linear dependence implies Wronskian is 0 for all x, so which is from the previous theorem. So in this implication it happens for all x, whereas for the converse statement, that is Wronskian equal to 0 for some x in I, then the functions are solutions of the ODE, then the solutions are linearly dependent. This statement is true. Okay, so let's prove this statement. So this implication, as we said, we have already proved in the previous theorem, which is 90. Okay, we don't see the numbers, but that is theorem 90. So this implication is true from the previous theorem which we showed, and that was true for all x. We need to prove the converse statement, this direction. Okay. So conversely, suppose the Wronskian is 0 So I'm just proving this result for the case when k is equal to 2 with the second order ODE here, but you can generalize it to any order. I mean, the idea is same. Okay, so suppose suppose a Wronskian at some x naught, since we need to assume this. So Wronskian is 0 at some point in the domain. Let's call that point as x naught. So Wronskian is 0 at x naught. Okay, we need to show that u1 and u2 is linearly dependent, where u1 and u2 are solution to a linear homogeneous second order ODE. Okay, so we assume that Wronskian is 0 at x naught. Now look at the linear combination alpha u1 x naught, beta u2 x naught. Okay, now we claim that at least either alpha or beta are non-zero. I mean, basically both cannot be 0. That's what we claim. That's what we need to prove. So how do you show that? So you differentiate this equation. So when you differentiate, you get alpha u1 prime x naught, u2 prime x naught. Okay, you differentiate that. Now when you write down the matrix, since the Wronskian is 0, we have a non-zero pair alpha, because from these two equations what we have is u1 x naught, u2 x naught, u1 prime x naught, u2 prime x naught. This matrix acting on alpha beta is equal to 0 0. Okay, so and the determinant of this at x naught is assumed to be 0. That means the determinant of this matrix is 0, which means the kernel of this should be non-trivial. That means there exists alpha and beta which are non-zero, right? At least there is a non-zero vector alpha beta such that this is 0. So we have a non-zero alpha pair alpha beta. Okay, this is from the assumption. So if you have a non-zero pair alpha beta, then you look at this function y. Define y as the linear combination of u1 u2 so for every x, right? So y is now a function of x is from I. So you look at so you take this alpha beta that you obtained earlier from the kernel of this matrix of, so this matrix u1 u2 u1 u2 u1 prime u2 prime. Okay, look at that y, right? Because we need to show that they are linearly dependent. That means we need to show that this y is 0. This y is 0 for all x, right? Because if this y is 0, so the y is the constant function 0, that means alpha u1 plus beta u2 is 0, where alpha and beta are non-zero pair, which means you have shown that linear. So you need to so we need to show that y is 0. Y is a constant function 0. So you start with this y. So now we don't know whether it's 0 or not. So you start with this y, which is a linear combination of this. Then you look, since u1 and u2 are solution to this differential equation Ly equal to 0. Okay, so by the linearity, L of y is also 0, where the y is this. Okay, so L of y is actually L of alpha u1 plus beta u2, and by the linearity of L, it's alpha L u1 plus beta L u2, but u1 and u2 are solutions, so this is 0, this is 0, so this is 0, so Ly is 0, so this Ly, so this y is also a solution to this second order ODE, right? But in addition, you also know y of x naught. Y of x naught is, you replace x naught here, and y of x naught is this, which is 0. Similarly, y prime of x naught is this. which is also 0. So is a solution to the initial value problem. Ly equal to 0. L is second order, right? Because we are taken 2, so k is 2 in this case. So it's a second order ODE, and you have two initial values, yx0 and y prime x0, both equal to 0. So y is a solution to this initial value problem, and we have already shown an existence and uniqueness result that, right, when the coefficients, so for a kth order linear homogeneous ODE, when the coefficients are continuous, then you have a unique solution. So in this case we assume this, and so here we are in a nice situation where the coefficients are continuous. So then this y, so if y is a solution to this initial value problem where the data is 0, that means the y should itself be the 0 solution, right? Which implies that y is, so with the uniqueness of the initial value problem, y is 0, right? So y is 0 where alpha and beta are non-zero. That means this linear combination is 0 for non-zero alpha beta, which means u1 and u2 are linearly dependent, right? So what is this X theorem has said? In general, this converse is not true, but if you assume that the functions are solutions of a differential equation, then the converse becomes true. Okay. So from this proof you should also observe that if you have linearly independent solutions of the linear ODE, then the Wronskian is non-zero everywhere. Okay, this is from the converse that we have already done, right? We will anyway show this in the following theorem. So what is the statement? If u1, u2 are again solutions of the kth linear homogeneous ODE in I, then the Wronskian of this collection of functions, either they are identically 0 on I or is never 0. What the statement means is that if u1, u2 are solutions of an ODE, then the Wronskian, let me take just two functions for simplicity, then it cannot happen that Wronskian is 0 for some x0 in I and the Wronskian is non-zero for some x1 in I. This cannot happen if u1 and u2 are solutions of ODEs, of some ODE. Okay, so what this statement means is that, I mean, if the Wronskian is 0 at some point, then it's 0 at every point of the domain. And if it's non-zero at some point, then it's non-zero at every point of the domain. Okay, that's what this theorem tells you. So what is the proof of this? It's actually, so if the Wronskian vanishes at some point, say x0, okay, then by the previous theorem proof, so 92 is the previous theorem, this theorem, okay, this theorem. From this theorem, so if it vanishes at some point, then from the previous theorem we know that u1 and u2 are linearly dependent, right? That's what the previous theorem said, that if they are solutions of some ODE, then if the Wronskian is vanishing at some point, then the solutions are linearly dependent. Now the earlier theorem, the first theorem that we showed, proved that for linearly dependent function, the Wronskian is 0 for all points in the domain. So which means if the Wronskian vanishes at some point, that implies linear dependence, and linear dependence implies that the Wronskian vanishes everywhere. Which is why if the functions are solutions of ODE, then if the Wronskian is 0 at some point, then it's identically 0. So a Wronskian is either the constant function 0 or it's a non-zero function. I mean it's never zero function. Okay. Okay. Let's look at some examples. So take this function u1 which is x and u2 which is sine x. Okay. Then what is the Wronskian of this? X sine x 1 cos x, sorry, okay, so Wronskian is a determinant which is x cos x minus sine x, and that's what I have written here. Okay, so the Wronskian of these two functions is x cos x minus sine x. Now this Wronskian is non-zero at say x equal to pi, right? Because at x equal to pi, sine pi is 0, cos pi is minus 1, so you get minus pi, right? So it's non-zero. So at x equal to pi, it is non-zero. So since the Wronskian is non-zero, the functions are linearly independent. This is from the first theorem that we proved, right? The case where linear independence implied Wronskian 0 every at all point, or conversely, if the Wronskian is non-zero at some point, then the functions are linearly independent. So the Wronskian is non-zero at some point. So these two functions are linearly independent. X and sine x are linearly independent. Okay. However, the Wronskian is 0 at x equal to 0. Right. So the Wronskian is non-zero at x equal to pi, whereas at x equal to 0, sine 0 is 0. Right. And cos 0 is 1. And whatever it is, x equal to 0, so it's 0. So the Wronskian is 0 at x. So this seems to contradict the previous theorem, right? Because the Wronskian of this function is non-zero at some point and 0 at some point, where the previous theorem tells you that the Wronskian has to be 0, either it has to be 0 everywhere or it's non-zero everywhere. Whereas here you have non-zero at some point and 0 at some point. So is it contradicting the previous theorem? No, it is not contradicting the previous theorem, because the previous theorem has this extra hypothesis that the two functions should be solutions of a differential equation, right? The two functions, so in this case, these two should be solutions of a second order linear homogeneous differential equation. Now that is not, and in this case that doesn't happen. X and sine x cannot span solutions of a second order ODE. Okay, I have given this in the assignment. Try to do it as an assignment problem. I have to show why x and sine x cannot span solutions of a second order ODE. Okay, so that's the idea of the previous theorem. So previous theorem tells you that in general Wronskian can be 0, non-zero at any random points, right? But if the functions involved, I mean the functions for which you are computing Wronskian, if they are solutions of kth order linear homogeneous differential equation, then the Wronskian is either identically 0 or it's never 0. Okay. Okay. Now let's look at another example of the second order ODE. And for the second order, we have already seen this ODE in various situations as examples. So for this ODE, sine x and cos x are two linearly independent solutions. Okay. Why so? Because if you compute the Wronskian, which is this, and the determinant of this is minus 1, which is non-zero. So the Wronskian is non-zero for all x in R. Okay. So So the Wronskian is non-zero for all x in R. So the first theorem tells you, right? So the first theorem tells you that the solutions are the functions are linearly independent. Okay, and what we have seen in the previous lecture is that these two are linearly independent by this property that we have checked, that their Wronskian is non-zero, and we have also checked in the previous lecture that sin x and cos x are solutions to the second order ODE, which means, right, and we have also seen a result in the previous lecture which tells you that for a second order ODE you can have at most you have exactly two linearly independent solutions, right? So you have two solutions which are linearly independent for this, which means there is no other linearly independent solutions other than these two for this ODE, right? Which means the general solution of this ODE, which means the general solution of this ODE can be written as linear combinations of sin x and cos x, right? Because you have two linearly independent solutions, we know it's second order, which means it has to be two-dimensional solution space. So, and they are generated by two linearly independent and which is sin x and cos x. So every linear combination of sin and cos is a solution to the second order ODE. Right? So if you recall in some previous lecture, we had said somewhere that we will show later in the lecture that every possible solution of this ODE is a linear combination of sin and cos, right? And that more or less we have shown here. Okay, now let's look at a different example, which is a third order differential equation, okay, which is this, right? Now we will show that e power x, e power minus x, and e power 2x are all three linearly independent solutions. We have also seen this example before, right? So we are now only checking that these solutions are linearly independent or not, which also we have checked before in a different way. So now what do we do to check this, whether they're linearly independent or not? Let's see, look at the Wronskian. So Wronskian is the determinant of this matrix. So if you compute the determinant, right, you get this, right? You have basically taken e power 2x common, okay, after some row operations, okay, not row operations, sorry, column operations. Okay, so what we have is Wronskian is this, which is non-zero, and this is non-zero for all x. So since the Wronskian is non-zero, which means that the three solutions are linearly independent. E power x, e power minus x, and e power 2x are linearly independent. Again, as I said before, it's a third order differential equation. We have already seen a theorem which tells you that for Ly equal to 0 for this operator, the solution space has to be three-dimensional. You have three linearly independent. So the general solution is just the linear combination or the linear span of these three functions. Okay. Okay. Now we are going to introduce the technique of reduction of order. Okay. What is reduction of order technique? This is a method where if by some guess or hook and crook, some way you are able to guess or know one solution of a differential equation, then using that one solution you can find a linearly independent solution corresponding to that. Okay, so if you know one solution, you can find a linearly independent solution corresponding to the given solution. Okay, and to do that we use the reduction of order technique. Okay, so you have a second order ODE, and we already know for a second order linear homogeneous ODE, the solution space is two-dimensional, right? So if you are given one solution, if I somehow by some means I can find another linearly independent solution, that means we have found all the solutions of this ODE, right? That's the advantage of reduction of order. So knowing one solution is enough to compute all the solutions of this ODE. So if U1 is a non-trivial solution of this ODE, okay, then U2, where it is just V multiplied to U1, where V is this, that U2 is a linearly independent solution. So it's linearly independent to U1. That is the theorem. So if you are given U1, you can find U2 which is linearly independent to U1, and what you have done to obtain U2 just multiplied V with U1, okay, and the V is given by this formula. So let's prove this theorem, okay. So what is that we need to show? So we are given U1, okay, we define U2 as U1 multiplied by V, and what this V or what we are multiplying with U1 we will choose appropriately in the following steps, okay. That we don't know yet, we will find out the formula for V. What is to be multiplied to U1 is something that we will derive in the process. So you start with U2, okay. Now what is that U2? And so you have defined U2. What is that we want from U2? We want that U2 is also solution to this ODE, right? That's what we want. We want a linearly independent solution. So we want it linearly independent to U1, and it should be solution of U2. So to substitute now, which means we should verify what is A, which means we want A2 U2 prime, A1 U2 prime, sorry, A2 U2 double prime, A1 U2 prime plus A0 U2 equal to 0. So for that we need to first compute the first derivative of U2, which is the product. We have used the product rule. Again the product rule, we have U2 prime. Now use this. So we want U2 to be the solution of this ODE. So we require U2 to be the solution of the given ODE. So we want this, right? We want A2 U2 double prime, A1 U2 prime plus A0 U2 to be 0. And we have already computed U2 prime and U2 double prime and U2 prime. And we also know U2 in terms of U1 and V. Use that information, right? If we use that information, we have and if we rearrange them, we get this, right? We have rearranged it in the derivative. So you have the coefficient of V2, V double prime, V prime, and V. Okay. So if you use this previous formula here, if you use this information and this information, you get this. Okay. Now here you see the coefficient of V. Coefficient of V, which is this, is nothing but the ODE that we started with. A2 U1 double prime, A1 U1 prime, A0, which we know is 0 because U1 is a solution to this ODE. So this is 0. So this term is not there. Okay. So what we are left is with only, so the coefficient of V is 0 because U1 is a solution, because U1 is already a solution to the given ODE. Which means what we are left with is this is equal to 0, right? Which is what we have said here. And that if you rearrange, you get this equation. Now this is easy to, now if you integrate, you can solve for V from here, because from here you get log V prime equal to minus 2 log U1 minus integral A1 A2. Okay, but here this 2, so this 2 can go as u square. Okay, if you can bring it this side, so this becomes plus and equal to, right? And now that becomes log of v prime u1 square, this, and that becomes v prime u1 square exponential of integral a1 a2, right? But what you want is find v, so bring the u1 square here, so remove the u1 square from here, divide both sides by u1 square, so you do u1 square. Now you have v prime, so now you remove this, now you integrate again, so what you have is v integral. Okay, and this is precisely the formula that you had here. V is integral of 1 over u square exponential of minus a1 by a2. Okay, that's what is your 5.1. So you have obtained your 5.1. Okay, just by solving. So you have this. Now what is that we need to show? Now we have found a u2 which is also a solution to the given ODE. What remains to be proven is that u1 and u2 are linearly independent, right? So we have found a v which is same as in the 5.1, the equation that I just showed you. Now we have to show that u1 and u are linearly independent. So for that you look at the Wronskian. u1 is u1, u2 is, by the way we defined u2, it's u1 times v, and its derivative, you can immediately see here that it is u1 square v prime. But u1 square v prime, we know from when we solved for v, we already know, so we already got it in terms of u1 square v prime, right? Here u1 square v prime is how we got it. So use that information, so we get exponential of something, and that exponential of that something should be non-zero, which means Wronskian is non-zero, which means u1 and u2 are linearly independent. So we were given u1, we found a u2 which is a linearly independent solution of the given ODE. Okay, this is a technique of reduction of order. Okay. Okay, so let's do an example. With that we will be done. So so let's take this ODE. Okay, this is a linear ODE, right? This is a linear ODE with variable coefficients. Now you can verify that the function x is a solution to this ODE. If you substitute x, if you substitute y equal to x in this ODE, you can see that it is satisfied. Okay, because y x, so x 1, so x double prime is anyway 0, so this term goes off, and then y prime is 1, so you get 2x, and y is x, so you get 2x with opposite signs, so it's 0. Okay, so x is a solution. So now using this solution x, we will find a linearly independent solution to this ODE, and this is second order, which means if I find a linearly independent solution, then we have then we have two solutions which are linearly independent, which means we know the entire solution space as a span of these two functions. So what is the other function u2? So what is that we need to do from the previous theorem? We need to write u2 as u1 times v, where u1 is x, So V, and V, there is a formula which we used, which was exponential minus integral A2. So this is my A2, so A2 is here, divided by A1, which is here, divided by A1, right? Then 1 by U1 square, U1 square is X, so X square, so integral of 1 by U1 square exponential of this. So you compute this, okay? If you integrate this, you see that you get V to be X minus 1 over X. So what is your U2? Your U2 should be U1 V, U1 is X, V is X minus X inverse, which is X square minus 1. Okay, so U2 is X square minus 1. Okay, so the general solution of this ODE is a linear combination of U1 and U2, which is this. So every solution of the second order ODE is of the form this. So that's the general solution. Okay, so yeah, so in that way we have solved for this ODE. Okay, so with this we will stop. We'll continue in the next lecture. Thanks a lot. See you. Bye.